Welcome back, and today I want to really get into what a Green's function is, what it's used for, and where it comes from. So let's give a little bit of history in this. Back in the 1800s-ish, there was Laplace, 1700s to 1800s, and one of his big questions, one's most known for, has to do with solving this equation. The derivative, or not the derivative, the Laplacian, as it were, of f is 0. That is, say, fxx plus fyy is 0 on a domain of some sort. Now, what this means, really, or in the terms we've been using, uxx plus uyy, it means that there won't be any maxes or mins, there won't be any saddle points, nothing like that. You'll have a smooth, calm flow going in the same way all along. And then if we add in a boundary condition of some sort, we now say this is some set D, and not only do we insist that del U is 0 in here, but we also insist that it be continuous at the boundaries, and it will converge to given values on the boundary of D. Then this gets renamed as the problem. You can call that Dirichlet, or you call it Dirklet. Man was born right on the French-German border, so you hear both pronunciations. So, when we are told we want to find a function that is harmonic, the Laplacian is 0 on an open set, and it converges continuously to some given values on the boundary, that's the Dirichlet problem. The canonical example of this sort of thing is heat distribution. That was, I believe, where Laplace started getting interested in the problem. That if we have no real sources of heat in an area, then the heat will just calmly flow through the room, the volume, the space, whatever, and it won't have any peaks or valleys. It won't all sink to one place. It won't all come from one place. Well, what this should make you think of is what we've been talking about with harmonic functions and the logarithmic potential. And that was where we were in around 1828 when along came a man named George Green. He strikes me as kind of a Van Gogh type. Maybe not quite that tragic, but he had virtually no formal education. He worked in a mill. He taught himself math by subscribing to journals. In 1828, he published what was essentially the foundation of potential theory. And so he was the first one to really give a mathematical framework for how electromagnetism works. But he wasn't really appreciated. He published a few things, and some physicists showed interest, but he didn't really get appreciated by mathematicians until after he died, thanks to Lord Kelvin in particular, who promoted his work. And it also ended up inspiring Maxwell, as in Maxwell's equations. So George Green is a big part of the history of electromagnetic physics and mathematics. So, the problem, to reiterate, is if you have some set where you want it to be the Laplacian is 0 everywhere, and known values on the boundary, then what is the function? And this is essentially where we get the potential function. We get it as a way of solving this problem. And it makes sense to think of this in terms of the Laplace problem and the Dirichlet problem, because our physical intuition all along has been we have some sort of charge on, that should not have been erased, sorry. We have some sort of electric charge on this, but it's allowed to distribute itself freely, so it all ends up at the boundary. And the potential is constant inside the whole thing. If you'll remember our diagram from a while back, we had this graph here where in the center the potential is at the highest, and it sort of flows downhill as you go outward. So it could be similar to having water on top of a hill and watch it flow away. So that's what we would expect, and so Green ended up developing the potential function as a way of solving this problem. So let's talk a little more about what exactly the potential function is and how it's useful. U to the mu of z. Well, what we've said all along is we want the equilibrium distribution. So once we allow the charge to spread itself out evenly, then the potential can be calculated with respect to that distribution, which is the integral of the log of 1 minus z t, absolute value, 1 over z minus t, d mu t. And we have established, thanks to Frostman, that this is equal to the energy of E quasi everywhere in the boundary of E. Actually in E itself, but in particular in the boundary, which is the condition of the Dirichlet problem. We know what it is on the boundary, and we know that this is harmonic outside of E. So that should start you thinking in terms of the Laplacian problem we have. Now, the quasi-everywhere thing means there might be a set too small to hold a charge. And if you go through the equation, capacity of, let's say, F, some small subset of E, is 0. We said E to the negative VE is 0 then. That's what capacity is. So VE equals infinity. And the way I think about that is you imagine there's, say, a spike here that's infinitely high. So the potential is infinitely high, so it can't possibly hold the charge because it will instantly roll downhill no matter what's around it. That should be F, not E. I'm sorry, I got my symbols mixed up. That should be VF. So F is some small subset of E that's too small to hold a charge. So what we know is that, except for maybe a very small piece of E, the potential is the same as the energy everywhere in there. Again, with this picture here, the potential is constant on here, on E itself, the disk. And there is sort of a converse to this as well. It says that if nu is a probability distribution on E, that is, it iterates out to 1, and has finite log energy, So the VE less than infinity. And we have that the potential with respect to nu is C quasi everywhere on E, then nu is the equilibrium distribution, equilibrium measure. So it's saying that if we have the equilibrium measure, we know the potential will be constant on E. And if the measure is constant on E, then it is the equilibrium measure. Or if the potential is constant on E, then it's the equilibrium measure. And I kind of analogize this to like if you are pouring water into a glass. If I say I have a glass of water, I start pouring into it, and it'll be kind of turbulent at first. It's settling in. It will not be all at the same level. Maybe it'll be higher up over here. But eventually, it will come to a nice level like this. And so once it's settled in to where it's the same level everywhere, that is the equilibrium measure. So I'm not going to try to prove this statement of converse because it seems intuitive enough. What I will try to prove is some stuff about the continuity of the logarithmic potential. So let's talk about that. So u to the mu e of z is harmonic outside the support of mu e. Support mean the places where it's non-zero. So E and maybe a little bit extra than E. So it's also continuous. Well, is it also continuous in the support of E, of mu E? Well, there's a good question. But there's a pretty straightforward chain of inequalities we can use to show this. We say u to the mu e of z naught for some point z naught in E. We just pick a point, or in support of mu e and E are close enough that I sometimes mix them up. Probably use either one in most cases, but let's just say support of mu e for now. Well, this is less than or equal to the lim nth as z approaches z naught of u to the mu e of z naught. Why is that? It's because the potential function was lower semi-continuous. If we didn't show that, just take my word for it, it's true, but I think we showed it at some point. Now lim inf is always going to be less than or equal to the lim sup, along the same thing. But then that, by Frostman's theorem, is less than or equal to the energy. Potential is going to be less, potential we've said is less than or equal to the energy almost everywhere. So if we have a lim sup, that means we can have a sequence converging, so that will have to be less than or equal to VE. It's probably easier than that. It's probably just that everywhere on mu E, the potential is less than or equal to the energy. So what we have here is we expect this to equal this quasi everywhere. That is what another bit of Frostman's theorem. So if they are equal, then the lim-inf and the lim-sup are kind of trapped between them, which means they're the same thing, the limit, which means that the limit z to z naught of u is equal to u, that should be z, these should all be z here, little mistakes that get you, mu e of z naught. And that's continuity. So, that gives us sort of a theorem we've just established here. And it's an if and only if. I'm not going to show all the details of that. I just don't think it's worth our time here. But, so it basically says u mu e of z naught, or z, is continuous at z naught in the support of mu e if and only if u to the mu e of z naught equals VE. So we expect it on the support of E to be equal to the potential at to the energy at most points. The potential and the energy are the same at most points in the support of E, of mu E. And so that is enough to give us continuity and vice versa. So now we're going to really break this down into what a Green's function is. So, we are going to say, first off, and define what it means to be regular, but we're going to sort of change our perspective here a bit. Let's say this is E. Then we're going to say the outer part of E is omega. So this omega is the unbounded component of C bar minus E. So these little bubbles are not part of E either, but we're not counting them. We're counting this part that's outside E and that goes all the way to infinity and includes infinity even. And what we will see is that the potential will be at a max here, as we've seen, on the boundary. And it will decrease as we go away from the boundary off to infinity. And eventually it decreases at approximately the rate of log of z. Which is probably not too surprising that it ends up turning into the very function that we've started with. But before, let's just give the quick definition that, let me clear this, well, yeah, being a little indecisive here. A point in the external boundary del infinity of E, so that's this boundary here, not the inner boundary with those two little blue blobs in the middle, but this outer boundary, is regular provided u mu E of z naught equals v of e. Otherwise, it would be irregular. And then omega is itself regular if all points on the boundary are also regular. So, we want to try to combine these things, and so that's what Green wanted to do here, to take a look at what's really happening here. So let's lay out some criteria of what a Green's function is. Well, for starters, we're going to say, again, with this way we're doing it, we've kind of been talking about E, which is a compact set, but we can also talk about omega, the outer boundary, the outer component is what I mean to say. And we're going to say, now a Green's function technically has two inputs, but we're going to fix one of them at infinity. That is to say, fix a pole at infinity. And that just means that as z gets close to infinity, we want the function to also go to infinity, as opposed to, say, picking some specific point in the complex plane and saying it'll go to infinity near that. So what we know here is a few things from this. And we're going to try to... Let's just go ahead and lay out what the criteria are. I go back and forth on what the best order to present these things in is. I'm trying to give some idea of how they were developed historically, but I more want to focus on getting the ideas there. G omega of z comma infinity is harmonic on omega not counting infinity itself. Infinity is a point, but we're don't have to be harmonic there. And bounded on neighborhoods away from infinity. So as this goes to infinity, the Green's function will get very small, but if we picked some random neighborhood that didn't get near infinity, it'll be bounded on that. Well, that fits the potential. As we saw, it just sort of rolls down through there, so there will be a lowest and a highest part on it. Now, we already know the potential is harmonic. We spent a lot of time in the last video showing that. Part B is G omega of z infinity minus the log of absolute value of z is on the order of 1 as z approaches infinity. I guess I don't really need the absolute value bars there. It doesn't make a difference. But, so that's just saying that the Green's function does not have to be exactly the same as log of the absolute value, but the difference between them is bounded. There is some constant whereby once you get a certain distance out there, it will always be smaller than that constant. The difference them will just get smaller and smaller. And C is just kind of a normalization factor. It's, maybe that's not the right word, but it says G omega of z infinity approaches 0 as z approaches zeta, which is in that boundary that we talked about, the outer boundary of E, which could also be called the boundary of omega, where Z approaches from the omega side. And again, that's quasi everywhere on that boundary. So we already have the Dirichlet condition says the boundary is something fixed. This is just saying it's going to be 0, which I think just makes the calculations easier. So the question now becomes, does the potential function satisfy all these things? Does it do what we want? Well, we know it does A right away. That's easy. We've established, it wasn't easy, but we established before that the potential function is harmonic outside of E. That's what omega is. And bounded, yeah. Yeah, we can say that. We saw the picture, but we can also say that if we had picked some neighborhood outside of here, there is some point, it's jumping around on me again, sorry. There is some point where this would be maximized. I'm thinking it would be whatever point is closest, and there's some point where it would be minimized. And so it is bounded. It's not going to go to infinity anywhere on that green circle. Criteria 2. Does it approach the log function? Well, the way I like to think of this, we think in terms of some basic physics stuff. One of the real foundations of Newtonian calculus was the idea of the point mass, that once you get far enough away from a complicated object, it acts just like a point. So as we get farther away, these points are relatively similar, these distances. In fact, I like to think if this is Z here, call the big distance capital M, the little distance lowercase m, you could say that capital M divided by lowercase m is pretty close to 1. And so I like to think of it as I am so far away from the thing that I don't even see the different pieces of it in the shape. I just see one big charge way off in the distance. And so if that's the case, then we've got u to the mu e of z is the integral log 1 over absolute value of z minus t d mu t. That is equal to the integral of the log of 1 over absolute value of z, absolute value of 1 minus t over z, d mu t. Now, we're saying let z be very large. Now, what happens to this piece if we let z get very large? Well, the t over z basically is negligible. And so that's just a times 1 on the bottom, so we drop it and we get the integral of the log of 1 over absolute value of z. Or Now this will then, since we're integrating d mu of t, not of z, this is a constant. D mu of t, much better. So that just equals negative log of absolute value of z. So then if I put a negative here and move the negative over to our side, we could say negative u to the mu e of z is approximately log absolute value of z for large z. So that is what we were trying to prove. Because we now have, well, hold on, let me think for just a second about what we're saying here. Yes, so the potential, we wanted to say g zeta of z infinity minus log of z is on the order of 1. And now what we have just shown is in fact not the potential itself, but the negative of the potential. The negative of the potential. So now our guess is maybe the Green's function is the negative of the potential. Well, it meets criterion B. It does approach the log of absolute value of z as we let z get large. And it meets criterion A because if a function is harmonic, its negative is also harmonic. What about C? What does it do near the boundary? Well, we know this from Frostman's theorem. If we have our boundary here, our E, and out here is omega, if we then approach it from the outside, negative u to the mu of E of z is going to approach negative v of E. The potential approaches the energy, Robin constant. So therefore, if our criteria C said we want it to approach 0, so let's add VE to our side. VE minus u to the mu of E of z, that approaches 0 as z approaches zeta in the boundary. And then if we went back to criteria B again, this is really what our Green's function is. So let's go ahead and define it in green. That's appropriate. It is the Robin constant, VE minus u to the mu of E of z. So at any point, the Green's function is we take that constant, the energy, and subtract the potential at that point. And so we can see, so that is, let's see. All right, so that fits. And so in some places we'll just immediately give you this as the Green's function. But to me, I think it made more sense to construct it this way as the solution to a problem that already existed. And that is with pole at infinity. You can rearrange this to have poles elsewhere, but mostly we're going to use one with the pole at infinity. So it's a bit complicated just to work it out, but sometimes we can get closed forms if E is not too complicated. We'll do an example of that. That way we wouldn't have to do an integral to evaluate it at any given point. There are a few obvious facts I want to touch on. First off, I want to talk about some terminology that's a bit inconsistent here. Because what we have here is E is compact, which means it's closed and bounded. Omega, open and unbounded. All right, so the Green's function I will sometimes write as E of z and call it the Green's function for E, or I might call it G of omega z infinity. Which really is it? Is it the function for E or the function for omega? And it really doesn't matter. It's kind of depends on your point of view. But the point really, I guess, is that it has to be harmonic outside of it in the open part and approach the set boundary to approach zero there. So I'm just saying, don't worry too much about the terminology. We're always assuming that is defined as being, what were the three criteria? On the open component, it is harmonic and bounded on neighborhoods that don't include infinity. And as you go farther and farther away from the compact set, it gets more and more looking like log of absolute value. And it's zero quasi everywhere on the boundary. In fact, there are a couple obvious facts there's one thing I really want to point at, which is that the Green's function will actually be zero quasi everywhere in E. And that's Frostman's theorem. Specifically, at all regular points of E. And once we're outside of E, we've said potential decreases outside of E. So the Green's function must be positive. You could even make this I don't want to necessarily say it would have to be a strict greater than, but at least greater than or equal to for Z that's not in E. Because we said it is the energy minus the potential. Since the energy is constant and the potential is decreasing as we go outward, that means it is going to shrink. It is going to get this piece, the potential, is going to decrease. So the Green's function will always have to be positive or at least non-negative outside. So you will never see the Green's function equal a negative value. It just does not happen because Frostman's theorem says the potential is always less than or equal to the energy. All right. That covers the basics. Next time we will do a few theorems regarding Green's functions, getting to know them better. I will see you then.